Yeah, happy to be here, also a bit humbled. I'm an ecologist, a biologist, doing species distribution modeling, and it's much, much simpler on the surface, I think, than all of these other models. But maybe I'll try to convince you also that it's the most important types of models you've never heard of. So what are these species distribution models? Basically, the idea is we want to know where a species can live. The way we do it is we have some observations of species, so it's the points in this slide. And we try to correlate where we find a species with often environmental variables or things like slope or the soil. And that way we can just build a model and say in what types of environments do we find this species. And of course, one very important application of this is climate change research, where we want to know not only where a species is found today, but where it's likely to be found in the future. So if you've heard that species are going extinct with climate change, or diseases are coming to new places, or invasive species are invading, these are the types of models we use actually for that. This is how we know. So I once explained this to a math professor, and then he said, "Isn't that just another word for regression?" And maybe some of you are thinking that, and I mean, in a way it is. We are regressing something. But it's also a big, big field of research. And over time, there are common standards, reoccurring problems like spatial bias. There's the same data sources that people are using again and again. So it makes sense to, build an ecosystem around this. We're just checking like this one foundational paper, methods paper. It's close to 20,000 citations. So it's really this huge field of research. And today, so these 20,000 citations, what are people, using to run these species distribution models? That's R. I mean, ecologists, they all use R. There are dozens of SDM packages in R. There are multiple that run entire workflows. And I mean, these work, right? Like, because there are so many people working in R, entire labs developing these things, they're very, very complete. Like every single thing you can think of, someone's implemented it. There's all these tutorials floating around, which makes it, super easy to start. And maybe it's good to say that, the average practitioner of SDMs, they're not in this room, right? They're not at this conference. They're first ecologists and second programmers. And so you run into these, big problems with R packages that no one is solving. Like, they're incredibly slow. Like, people will be running these for a month on a cluster, even though they're just running some pretty simple models, and the syntax is not great, and the customizability is very bad for a lot of these tools. So we're trying to do it in Julia, and already when we started in the train on our way to Copenhagen, we said, okay, we don't just want a package. Like, as much as possible, we should make this possible by committing to existing packages like Rasters. And we rely a lot on MLJ, the MLJ ecosystem, to make this work. And then we make this one package that, the ecologists can understand, and they will build on both MLJ and Rasters and kind of bring it all together and make it as easy as possible to make SDMs. So just let's do an SDM. I chose an Australian species because Australia is nice and isolated. Eucalyptus regnans. It's the tallest flowering plant in the world. And it's actually kind of threatened, so it's not totally irrelevant to want to know. And now we'll just do a quick workflow and see if we can make an SDM for this species. So the first thing we want is some environmental data. So I use rasters, and I use raster data sources. And these are easy to just download from the web. Now I'm just using temperature and precipitation as a covariate. So this is what it looks like in Australia. Most of it's dry, some of it's wet, most of it's warm, some of it's cold. That's Australia, right? And then the next thing is occurrence data. So here we're using GBIF. It's this big collection of occurrence data. People took a picture of a tree and uploaded it with their location. We're downloading all of those observations. And then we're doing this very typical thing, which is spatial thinning. If you found one tree of a species, probably there's another one right next to it and another one right next to it. And we don't want the entire forest in the model. So with the thin 5,000, we're just saying we're removing random points so that all of them are at least 5 kilometers away from each other. It's one of these, classic things that people just started doing because it works. And then we need something to regress against. We can't just have presence points. So there's also a classic thing. We just say we have our presence points, and then we sample random background points from Australia. So we're teaching our models to know the difference between a location where we found this eucalyptus species and a random point in all of Australia. And again, this is what it looks like. In the gray, we have random points. And in red, we have places where our eucalyptus species was found. And now is where the species distribution models package comes in. We just make some data objects where we already do our cross-validation and put all of the presence and background data together in one object. And it prints some useful information, like how many folds we have and what kind of predictor variables, so we can check that this all works. Then we need some models. And one very, very common thing to do with these in this discipline is to take multiple models, fit all of them, and then take the average at the end. So here we're using MLJ. We're using a Maxent model, which is very popular, a boosted regression model, and just a GLM. And we fit the entire thing by just calling SDM on the data object we just made and the name tuple with the models. And then it just fits all of them. I mean, that's MLJ, just calls MLJ in a loop and fits all of them. Of course, we want to know if this works. So again, we just called SDM.evaluate on the model, and it tells you for the train and the test data the performance of the individual models and of the entire ensemble. In this case, it's like 0.98 AUC or something. It's a very easy species I chose. And then we predict. Again, it's just SDM.predict. We just want to reduce by taking the mean of all of them, and then this is the map we get. I mean, not so surprising, given that this is where the species lives. So in the south over here is where our models predict that the climate is suitable for the species to survive. And if we want to do, I didn't do it now, but if we want to do for the future, a climate change scenario, we just predict to a different set of climate predictors for the future. And then there's a few cool things, like we want to kind of know why, in many cases, the model predicts the way it does. So we can explain and call Shapley values, and we see that, for example here, this is interactive, not right now, but it can be interactive. The colder it is, the model favors cold environments. Yeah. So this all kind of works. But we need to get all those R people, the 20,000 of them, to come over to Julia and start using this. So what do we need for this? Well, I think this package is, hopefully makes it easy enough for them, but it's still early stage. It needs to be more complete and more documented. We need all those pros that R has, right? And then we also need the cons to not be there in Julia. We have all these models in MLJ, and we can interface with them pretty easily. We have these raster packages, which is great. But I think what we need is, tutorials across the packages to make people understand this. Also people who aren't, first coders, but first ecologists, then coders, programmers. We need all the tools in Julia, like GAMs are something we don't have in Julia right now, and it's kind of a must for this kind of modeling. And yeah, we've been talking about that in the geo ecosystem, the syntax sometimes isn't as intuitive as it could be. So I think it's also something we might need. That's it. Thank you.
Are there any questions?
First, a comment to your last point about the tutorial. So tomorrow is the hackathon, so I'll be happy to sit down with whoever's want to work on tutorials on the Julia Geo ecosystem. And then a question, could we inverse this? So say we have a distribution of species and predict the climate from that?
I guess. I don't know. It's not something ecologists do, right? Ecologists are mostly interested in the other way around.
So what makes this unique to ecology? There's something in the species distribution, like a distance function or something, that makes this unique to species?
No, it's just another word for regression, right? I mean, you know, you can see the math professor classes. You have them on right now, and then it's just another regression. Again, I think it's like, it's a field that has developed. And so people have kind of started agreeing on that the best way to do this is, for example, to fit 5 models and take the average and not just fit 1 model, right? So there's these kind of common tools, common models that you could use in all kinds of problems. But people have found out or agreed on that we should use them for this model. So, but no, I don't think there's anything, you know, fundamental about, fundamentally different. No.
Okay, I'll make it very fast. It was very interesting. I have no idea about the topic. And my question is, there's actually a time component in the problem, right? I mean, if I start cutting trees and then I stop, the climatology didn't change, but I did a perturbation that needs some time to recover. Is that something your package can embed at some point? Is that something that people don't do in species distribution modeling?
I mean, people add predictive variables like a human perturbation index or these kind of things to have human influence. But it builds on this biological theory that for every species there's a set, you know, there's a n-dimensional environmental space where it can live. And that's the kind of the space we're trying to find with all these models, right? So you're not always predicting where you find it, but where it can be found or where it can live, right? So that's the kind of theoretical.
Okay, another round of applause, please.